When exploring the mysteries of the universe, physicists are like two different expeditions. A research team follows in Albert Einstein's footsteps, exploring the grand beauty of the universe through the lens of general relativity and modern telescopes. The remaining group joined Niels Popper and Werner Heschenberg to explore the mysteries of the microscopic world through a quantum mechanical microscope. These two theories are the foundation of modern physics, like a pair of mirrors reflecting the universe. Reflecting every facet of the universe, from the microcosm to the macrocosm. The theory of general relativity, exploring the grand picture of the universe, uses gravity as a key to understand the curvature of space-time and how it shapes the large-scale structure of the universe. Einstein's theory of relativity is like a magnificent cosmic painting, unifying the motion of stars, planets, black holes, and the entire universe into a single frame of reference. However, when zooming in to attempt to capture details at the quantum level within the framework of general relativity, the image becomes blurred. On the other hand, quantum mechanics researchers are playing a crucial role in the microscopic world. This theory demonstrates the dual nature of matter, exhibiting both particle and wave characteristics, while also addressing the famous uncertainty principle. Quantum mechanics not only helps us understand the behavior of atoms and subatomic particles but also serves as the key to exploring chemical reactions, physical phenomena, states of solid matter, and even the processes occurring within living organisms. But trying to study the entire universe or massive objects like black holes using quantum mechanics is like using a microscope to observe galaxies. Behind the dazzling successes of general relativity and quantum mechanics lies an undeniable truth. They have never adapted to the harsh conditions described in the universe. When scientists attempt to apply these two theories to extreme environments like the Big Bang or black holes, they find them to be in conflict. The concept of continuous spacetime in general relativity appears to no longer hold at the quantum scale, where the randomness and uncertainty of quantum mechanics dominate. I've never really been fond of macroscopic determinism in general relativity. This incompatibility is no trivial matter. It challenges our most fundamental understanding of the universe and compels the scientific community to seek a unified theory. Can both describe the overall structure of the universe and reveal its large-scale operating mechanisms. This theory is called quantum gravity, with the goal of constructing a new model of the universe to seamlessly connect the cosmological perspective of general relativity with the microscopic world of quantum mechanics. Imagine the universe as a giant rubber sheet. General relativity is the tool that helps us understand how it works. The planets and other celestial bodies are like heavy objects placed on this sheet, causing the rubber sheet to bend inward. That bending is what we call gravity. This is not just a metaphorical expression, but the very essence of the general theory of relativity published by Einstein in 1915. The curvature of space-time describes the gravitational relationship between masses. What's even more astonishing is that this theory not only explains the orbits of planets around the Sun but also predicts the existence of black holes. And the expansion of the universe was later confirmed through empirical observations. But general relativity doesn't just predict the motion of celestial bodies. It also paints an extraordinarily spectacular picture of the cosmos at large. In this painting, the universe appears incredibly dynamic. It can expand, contract, and even reach a singularity with infinite density within a black hole. It is the description of the universe's extreme states that has made general relativity the foundation of cosmology. However, just as we marvel at the grand beauty of the universe through general relativity, a quiet problem emerges. When we attempt to apply it to describe the most fundamental components of the universe, that is, phenomena at the quantum level. This magnificent painting seems completely contrary to the macroscopic world we are observing. Like trying to interpret Impressionism through a classical landscape painting, both depict the same world, but with entirely different languages and techniques. This mismatch is sometimes not a cause for concern. On the scale of everyday life, we cannot observe quantum fluctuations or perceive the curvature of spacetime. But when we focus on the extreme phenomena of the universe, such as black holes or the Big Bang, the incompatibility of this theory has become an obstacle that cannot be ignored. General relativity provides a clear understanding of the universe on a large scale, but that perspective becomes blurred when approaching quantum phenomena. Like an old man gazing at distant stars through a telescope. When a curious child asked him about the mysteries of the microscopic world through the microscope, he stood silently, unable to utter a word. This limit reflects our incomplete understanding of the universe. That is precisely the issue Li Tuyen aims to resolve through quantum gravity theory. Stepping into the world of quantum mechanics is like wandering into Alice's Wonderland, where every rule defies the ordinary intuition of our daily lives. That is a world where a grain of sand can exist in multiple places at once, and the cat is both dead and alive simultaneously. At least until the box is opened, the act of observation by the viewer can alter the outcome of physical phenomena. These things may sound as mysterious as magic, but in reality, they are fundamental phenomena in quantum mechanics, such as quantization, wave-particle duality, quantum states, and the observer effect. Quantum mechanics emerged in the early 20th century as a theoretical framework describing the behavior of microscopic particles such as electrons and photons. The passage explains why atoms do not collapse, the process of molecule formation, and the nature of chemical reactions. What's even more astonishing is that quantum mechanics can predict many phenomena that are hard to explain, such as quantum entanglement. Two particles can instantly influence each other, no matter how far apart they are, as if connected by a mysterious bond that transcends all barriers of time and space. However, although quantum mechanics is extremely successful in describing the microscopic world, its language is entirely different from that used by general relativity to describe the macroscopic universe. If general relativity is a refined gentleman in a formal suit, calmly conversing, then quantum mechanics is like a free-spirited artist, unrestrained and full of wondrous magic. Both descriptions reflect the reality of the natural world, yet they stem from distinct perspectives and modes of expression. This difference is not just a philosophical matter to ponder, but also has serious practical consequences. When attempting to apply quantum mechanics to describe gravity, a force that may seem feeble in everyday life yet governs the entire universe, we face no small challenge. At the quantum level, gravity is no longer continuous or exists within a smooth spacetime, but becomes a phenomenon of discrete particle jumps. Combining the particle-like nature of gravity with the continuous curvature of spacetime in general relativity is as difficult as forcing a free-spirited artist to adhere to strict classical aesthetic rules, an immense challenge. Thus, the world of quantum mechanics is both vibrant, mysterious, and full of potential, while also creating a vast gap in scientific understanding when attempting to connect with the cosmology of general relativity. This crack is precisely the point where quantum gravity theory emerges to resolve. Though the path ahead is fraught with thorns, it is our courage and the yearning to uncover the unknown that drive us ever forward, striving to unravel the deepest mysteries of the universe. The conflict between black hole singularity and the information paradox. Singularity. First, let's discuss this particular point. In general relativity, a singularity is the location at the center of a black hole where both the density of matter and the curvature of spacetime become infinite. By this definition, a singularity is like a bottomless abyss in the universe, where everything that falls into it vanishes completely, including information. However, quantum mechanics rejects such an approach. In the quantum world, information is considered to always be conserved, much like energy and matter. This principle is the origin of the famous information paradox. If information falls into a black hole and is destroyed at the singularity, the fundamental principles of quantum mechanics would be violated. Stephen Hawking once proposed that black holes could emit particle radiation and gradually vanish due to evaporation. But this leads to another question. When a black hole evaporates away, what happens to the information that fell into it? This question is not merely an intellectual challenge, it strikes at the very foundation of physics itself. If information truly disappears into a black hole, our universe would become an unpredictable place. And the predictive capability of quantum mechanics would significantly decline. And if information is not lost, how can it escape from a black hole's singularity as described in general relativity? Faced with this challenging problem, physicists have proposed various hypotheses and theoretical approaches to find a solution. One of the fascinating ideas is a viable solution to the black hole information paradox, which involves the phenomenon of quantum entanglement. Some particles may escape the black hole while still retaining information about the particles that were pulled inside. Spooky action at a distance. It is precisely these difficulties and paradoxes that have driven the development of quantum gravity theory. Scientists realized that to solve these problems, an entirely new theoretical framework needed to be constructed. Can describe both the macroscopic phenomena of the universe and the microscopic phenomena in the quantum world. Black holes are not only the most extreme entities in the universe but also the harshest laboratories for theoretical physics. Challenging our understanding of the most fundamental laws of the universe. The journey to discover quantum gravity. On the vast stage of physics, quantum gravity theory was only added later. Its mission is truly extremely difficult. To resolve the conflict between general relativity and quantum mechanics, while establishing a unified theoretical framework for both. It sounds like painting shimmering stars across the sky and tiny, lovely whirlpools on a blank sheet of paper. The journey to uncover the theory of quantum gravity is far from solitary, as many scientists are working together to find the solution to this problem. On their journey of discovery, physicists have proposed numerous diverse hypotheses and models to build a comprehensive theoretical framework. It can describe both the grand phenomena of the universe and the tiniest of phenomena. From string theory to loop quantum gravity, and then to studies on black hole entropy and Hawking radiation. Each step feels like discovering an entrance to a hidden world within the boundless forest of the universe. Let's explore string theory together. This is likely the most famous candidate for quantum gravity theory. According to string theory, the fundamental components that make up the universe are no longer point particles. Those are the tiny silk threads vibrating. The different vibrational patterns of these strings determine their roles as fundamental particles, such as electrons, quarks, and so on. The allure of string theory lies in the fact that it doesn't merely seek to unify all fundamental forces. Not only does it encompass gravity, but it also predicts the existence of additional spatial dimensions. However, one of the greatest challenges of string theory is its extreme mathematical complexity. And there is currently no direct experimental evidence to prove that. Another approach is loop quantum gravity, an attempt to directly quantize spacetime. Unlike string theory, loop quantum gravity does not require the addition of extra spatial dimensions or assumptions about new fundamental particles. And its starting point is close to the original structure of quantum mechanics and general relativity. Loop quantum gravity describes a spacetime composed of interwoven quantum loops. Gravity arises from the interaction between quantum loops. This approach offers fresh insights into the primordial state of the universe and the mysteries hidden within black holes. But this theory also faces challenges in experimentally verifying its predictions. Another important milestone in the journey of exploring quantum gravity is the study of entropy, black holes, and Hawking radiation. Through numerous studies on black holes, scientists have discovered that black holes are not completely black. They emit particles due to quantum effects and eventually evaporate completely. This discovery not only unveils crucial clues about quantum gravity but also proposes a viable solution to the black hole information paradox. Here are the natural English translations for your options. Amid the misty journey of exploring quantum gravity, string theory stands like a lighthouse, illuminating the yet unsolved mysteries. This theory presents a surprising idea. Everything in the universe, from the shimmering stars in the sky to the tiniest particles of matter that make up the human body. Essentially, it is composed of minuscule vibrating strings. The way these strings vibrate will determine their operational characteristics. Like the different strings on a guitar, each one produces a sound with its own distinct tone. The appeal of string theory lies in its ability to not only explain the structure of matter but also to unify the four fundamental forces of physics. The strong force, the weak force, the electromagnetic force, and the gravitational force. In string theory, these seemingly distinct forces are actually just different manifestations of the same entity, vibrating strings in various ways. It sounds almost like magic, but mathematically, this is indeed a feasible way to unify quantum mechanics and general relativity. Even more intriguing is that string theory predicts the existence of additional dimensions in the universe, far beyond our understanding of three-dimensional space and one-dimensional time. These hidden spatial dimensions open up an entirely new understanding of the fundamental structure of the universe, and may well be the key to unraveling the mystery of quantum gravity. However, the existence of these extra dimensions makes the physical predictions of string theory difficult to verify directly through experiments, leading to much debate within the scientific community. Although string theory possesses an exquisite beauty and poetic charm, it has not escaped criticism from the scientific community. One of the most criticized points is that, to this day, we still cannot directly observe the extra dimensions or the strings themselves. This leaves string theory in a dilemma, as some scientists argue that it resembles mathematical structures more than a verifiable physical theory. Additionally, the extreme complexity of string theory is also a major obstacle. This theory itself requires a very advanced level of mathematics. The concept of the multiverse, once predicted, has sparked philosophical debates about how science should test hypotheses. Nevertheless, to this day, string theory remains one of the most promising candidates in the quest for a unified theory of the universe. This passage suggests a potential connection between quantum fluctuations in the microscopic world and spacetime curvature in the macroscopic world. The theory of quantum gravity is presented from a different approach. If string theory deciphers the mysteries of the universe through minuscule vibrating strings, then loop quantum gravity offers a distinct perspective. A direct quantization effort of spacetime offers a completely different perspective to explain the universe compared to string theory. Imagine general relativity describing spacetime as an endlessly shifting elastic fabric. The theory of quantum gravity reveals that this fabric of spacetime is actually woven from countless minuscule, discrete quantum loops. This idea presents us with a detailed framework of the universe, challenging our conventional understanding of spacetime continuity. The appeal of quantum gravity theory lies in the fact that it does not rely on unobservable extra dimensions or undiscovered physical entities. Instead, it was developed based on existing knowledge of quantum mechanics and general relativity, and try to explain gravity in a simpler and more understandable way. The loop quantum gravity theory presents an intriguing prediction through the quantization of spacetime. At extremely small scales, spacetime has a discontinuous structure. The quantization of spacetime opens new avenues for understanding the primordial state of the universe while unraveling the mysteries within black holes. Loop quantum gravity theory also offers a unique perspective in explaining the black hole information paradox. If time is not composed of quantum particles, then the singularity in a black hole would. A point with infinite density is, in theory, impossible to handle and may not exist at all. Instead, the center of a black hole could be a giant quantum vortex. Information is not destroyed but preserved or transformed in some way, while quantum gravity theory offers us a fresh perspective on the universe. It also faces its own challenges, much like string theory. Predictions about loop quantum gravity are very difficult to directly examine in the current state of this field of science. Moreover, this theory itself is still in the process of refinement and has many unresolved issues that need clarification. For example, how to fully integrate all components of quantum mechanics, and how to derive accurate cosmological predictions from that theory. Additionally, quantum attraction opens up a new perspective on the universe for us. It also has to face its own challenges in our new perspective. Moreover, quantum gravity provides the fundamental elements of quantum mechanics, and how to fully integrate all elements of quantum mechanics. Moreover, quantum gravity also provides the fundamental elements of quantum mechanics. And that's it. That's how it is. Tony felt it the same way Albert King once did. Like catching sight of light in a darkened room, revealing a possible path to unify gravity with quantum theory. First, let's discuss the entropy of a black hole. Traditionally, entropy is a physical quantity that represents the degree of disorder in a system. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This idea may sound counterintuitive, but it actually reveals crucial information. The amount of information a black hole contains is proportional to its surface area. It's not its density, but rather its alignment with the three-dimensional principle in information theory. Black, and emits particles in the form of Hawking radiation. This discovery shocked the scientific community because it revealed that black holes would gradually lose mass and then vanish completely. A process that appears to defy the principle of information conservation. Hawking radiation not only helps us understand how quantum effects influence strongly gravitating objects. At the same time, it also provides crucial clues to help resolve the black hole information paradox. Research on black hole entropy and Hawking radiation has forced physicists to reconsider many previous perspectives. How quantum mechanics and general relativity can coexist under extreme conditions. These findings have demonstrated the fundamental laws governing the universe. Hidden behind these seemingly simple equations may be secrets waiting to be uncovered. Diving deeper, they reveal to us the intersection between the quantum world and gravity. Things may be closer and more complicated than we imagine. Through the study of black hole entropy and Hawking radiation, scientists have been gradually constructing a theoretical framework for quantum gravity. These studies not only help us gain a deeper understanding of the nature of black holes. At the same time, it also offers new perspectives and solutions to resolve the conflict between quantum mechanics and gravity. It is that very courage and curiosity that drives humanity to explore the fundamental principles of the universe under extreme physical conditions, has propelled the field of physics and indeed the entire scientific community forward. Real-world experiment to verify quantum gravity. Exploring quantum gravity theory is like groping for a way out in a pitch-black underground maze. And though the lighthouse of theory lights the way, it lacks the support of experimentation. We cannot say for certain that we are on the right path. This has a profound impact on research in quantum gravity. How can these highly abstract mathematical theories be verified experimentally? First, we need to address the technical challenges. The effect of quantum gravity is extremely weak under normal conditions. With current technology, direct observation is very difficult. For example, string theory predicts the existence of additional spatial dimensions. Just like the space-time brains-in-loop quantum gravity theory. In order to be detected, it requires an extremely large amount of energy. An energy level unattainable by particle accelerators on Earth. Moreover, the intensity of Hawking radiation signals is direct evidence that the black hole is evaporating. So low that it is nearly undetectable against the cosmic radiation background. However, scientists remain persistent and refuse to give up. They are continuously researching, developing new techniques, and designing experiments to achieve the set goals. Indirectly observing the effects of quantum gravity. A feasible approach is through sophisticated astronomical observations. For example, in the extra-spatial dimension predicted by string theory. The scientists hope to uncover some clues. For loop quantum gravity theory, scientists are studying the possibility of measuring the granularity of spacetime. By searching for distinctive signatures in the cosmic microwave background radiation or not. Meanwhile, some theoretical researchers are also considering more groundbreaking and bold experimental designs. For example, applying the black hole information paradox. Design thought experiments to test whether information can truly escape a black hole. Although these experiments are still only theoretical and computer simulated at this stage. But they open up feasible research directions for future experimental physicists. The experimental study of quantum gravity is not only the key to testing the accuracy of the theory. That is also the only path for physics to advance. Every breakthrough step in the experiment opens a new chapter for the field of physics. Explore the deep structure and fundamental laws of the universe. Despite the challenges, countless scientific discoveries throughout history have proven just that. It is our endless curiosity and desire to explore that will lead us to the light at the end of the path. And unravel the deepest mysteries of the universe. The boundary between theory, the Big Bang, and the harsh conditions of the universe. In the theater of physics, the Big Bang is not merely an explosive beginning. At the same time, it is also the ultimate challenge to the limits of theory. This segment discusses the origin of the universe. Put the two superstars of general relativity and quantum mechanics on the same stage. Only to realize that there are irreconcilable differences between us. The Big Bang explosion and the extreme conditions in the universe created an exceptionally unique environment. To test hypotheses about quantum gravity theory, they force us to reconsider the true nature of time, space, and the wisdom of the universe. We must reconsider the nature of time, space, and even matter. According to the general theory of relativity, the Big Bang marks the beginning of space, time, and matter. But when we apply this theory to trace back to the primordial moment of the universe, singularity, a theoretical point where density becomes infinite and the laws of physics no longer apply. General relativity has reached its limit in explaining this moment, because it cannot handle the infinite density at the singularity or the infinite curvature of spacetime. Quantum mechanics offers a completely fresh perspective on this issue. It implies that at the smallest scale, the universe operates through quantum fluctuations. Perhaps the singularities were avoided in the conventional sense. However, quantum mechanics itself does not possess all the necessary tools to describe phenomena occurring under conditions of extremely high matter density and enormous energy like that. In other words, at the very moment the universe came into existence, the laws of physics seem to collectively cease functioning. By providing a unified framework between quantum mechanics and general relativity, the quantum gravity theory is expected to explain the primordial state of the universe, and explain the process by which the universe formed from nothingness to become an entity existing under these extremely harsh conditions. This holds significant importance in understanding the origins of the universe, while also potentially revealing new forms of physical laws under extreme conditions. However, exploring Li Tuyet was far from simple. This requires the development of entirely new mathematical tools and concepts in the field of physics. May involve the quantization of time and space, or perhaps, entirely different conceptions of how the universe was constructed. Every new step unveils a journey to explore the unknown, and every groundbreaking advance by Li Tuyet could unveil fresh insights into the nature of the universe. The Big Bang explosion and the extreme conditions in the universe not only push the limits of our theories to the brink of challenge, while also fueling the desire to explore and gain a deeper understanding of the universe within us. The theory of quantum gravity plays an extremely important role in this discovery, not just stopping at the hope of reconciling the conflict between general relativity and quantum mechanics, but also the key to unlocking the mysteries of the universe in extreme states. As we continue researching in this direction, we may uncover the mysteries behind the Big Bang. and understand the true story of the universe born from nothingness.